Hi there. In this video we're going to have a look at the math behind a secret Santa party. So this is a party where each participant in the party is going to give a present to one of the other participants, and the way to allocate who is going to give a present to whom is traditionally by writing the names of all the participants on little notes, putting those notes in a hat and having everybody draw one note or one name from this hat. And we typically do this with friends, for instance, around Christmas, or in my country around the Feast of St. Nicholas. Now, a problem that you might encounter in this case is that somebody draws their own name, and that's of course not what you want. So if that happens, if anybody draws their own name, you will start again and start this procedure of drawing names from the hat once over. So the question that I'd like to address here is, what's the probability that this happens, or in other words, how often would you have to restart this procedure on average? Well, you can imagine that this is going to depend on how many persons are in the party. So if you're doing this just with your two friends, so 3 people, I'm sure that you can convince yourself that there's in 1/3 of the times nobody will actually draw their own name, and 2/3 of the draws will result in at least one person drawing their own name. But the question is, if you do this with more people, so perhaps you're doing this with 10 of your friends, or with all the 100 people in your street, or with 1,000 people in your school. So what's going to happen? Is it still probable that somebody is going to draw their own name? Well, you might imagine on the one hand, the probability that you will actually draw your own name is pretty small if you're doing this with 1,000 people. But on the other hand, there's 1,000 people, so that's sort of, each of these people might actually draw their own name, so that's working against it. So which of these intuitions is going to dominate, or are they going to cancel? Well, we're going to look first in this video at a computer experiment where I'm going to do this drawing of names from a hat with a computer a lot of times, 1 million times, for different numbers of people in the crowd, in the group. And we'll figure out actually that this latter thing occurs. These two infinities are going to cancel each other if you grow the number of people in your party. And actually there's a finite probability that no one will, probability between 0 and 1, that is, that no one will actually draw their own names, but there's also a fixed, ultimately a large probability that at least somebody will actually draw their own name. So if we look a little bit more closely, what is suggestive of this result is actually that this probability tends, as the number of people in a party grows very large, to a very special number. So we'll see what this special number is. And then actually the larger part of this is in computing this particular number. So what we'll do is first we'll have a look at, let's just write out, what's this probability for low numbers of people in this group, and then we'll try to sort of generalize this to larger numbers. And the technique that we're going to use for this is that of creating a generating function. So a generating function basically means that we are going to transform this problem, which is a problem essentially of counting numbers of ways in which you can allocate these different names among all the people in the party. It's a counting problem. We're going to transform this into a problem having to do with continuous functions. Functions which you can actually do calculus on. So that means we have the tools, the powerful tools of calculus actually to solve a problem related to discrete mathematics, to mathematics of counting. So the motivation for this is first because we would like to know more about secret Santa parties perhaps, but the secret hidden agenda here is that I want to illustrate using this example the power of looking at these things through the lens of a generating function. So here's a report basically of a computer experiment that I did. So what happens here is that the computer is going to do this drawing of names from the hat for us, not just once, but a lot of times, 1 million times actually. for each group of players. So what you see on the horizontal axis here is the number of players. So the leftmost bar is a party involving only 2 persons, and what the computer is going to do is draw names for those 2, allocating who's going to give a present to whom among those 2 persons. Do this a million times and just check out how often it happens that nobody draws their own name. And as you can imagine, and might have anticipated, in half of the times actually both players will draw each other's names, whereas, which would be a good outcome, whereas in the other half of all the draws they would each pick their own name. So the probability of no self draws here would clearly be a half, and that's actually what the computer reproduces by just doing this lots of times. So that next bar is 3 persons, so you can perhaps convince yourself that with 3 persons it is 1/3 of the times that people are going to, that nobody's actually going to draw their own names, and that's actually also the outcome of this computer drawing. What happens if we increase the number of players? I'm doing this here again, having the computer draw names for 10 people, for 100 people in the group, or for the really large party of 1,000 people. What you see is that the probability that no one draws their own name among all these players actually seems to converge to some finite value between 0 and 1. So what is this finite value? Well, it turns out to be approximately 0.3678. So let's see what that means. So the probability that no one draws themselves is 0.3678, more or less. So is this number that you recognize? Well, actually I didn't when I first saw this number, but what's perhaps a more intuitive number is how often would you have to redo the drawing of names from the hat in order to get nobody to get their own names? Well, that's 1 divided by this probability, right? So that's 1 divided by this 0.3678 probability. Well, this is perhaps a number that's more recognizable. Actually, it's fairly close to, well, perhaps the second most best known number apart from the integers that we know, because it's very closely related, as you might recognize, to the number e. So e, the mathematical constant e, Euler's constant, is 2.7182. So it's close to this number that we have here. And indeed, if you make the number of draws from the computer by the computer larger and larger, and also the number of players in this group larger and larger, indeed this number seems to converge to 1 divided by e. Well, let's next have a look at this problem analytically on paper for small numbers of partygoers in each group, and try to check to compute probabilities of having no self-draws for these different smaller groups. And let's start at n equals 3. So we have 3 players, 3 participants in the party. We're going to analyze the number of ways in which these 3 people, Alice, Bob and Charlie, can actually draw a name from the hat such that either there is no self-draws as equals 0, in which case none of these 3 is going to draw their own name, or 1 self-draw, 2 self-draws, or 3 self-draws. Well, obviously, so we look at this a little bit already in the computer experiment. So for s equals 0, so nobody draws themselves, there's 2 ways in which this can happen. So Alice is drawing Bob, Bob is drawing Charlie's names, and Charlie is drawing Alice's name. or Alice is drawing Charlie's name, Charlie is drawing Bob, and Bob is drawing Alice. So there's two different ways in which this can happen. Similarly, if we're having one self-draw, it could be Alice who draws herself, her own name, Bob and Charlie drawing each other, or the other three combinations. So there are three different ways in which we can have one self-draw. If you think a bit, having two self-draws but not three, that's actually impossible. There's no way in which this can happen. But indeed, everybody, Alice, Bob and Charlie drawing their own name, that's a possibility. That's just a single way in which this can happen. But let's try to actually expand this to a slightly larger group, n equals 4, and see whether we see a pattern emerging. So for n equals 4 people in the party, let me skip for a little bit the case in which s equals 0, so nobody draws their own name. But let me first focus on the case in which there's just one person, say Alice, who's going to draw her own name. In order for her to be the only person drawing her own name, we need Bob, Charlie, and Dennis, the fourth person in this group, not to draw their own names. So Bob, Charlie, and Dennis, they together form a group of 3, and we know in how many ways actually 3 people can avoid drawing a name out of their groups. We just computed that. That was possible in 2 ways. So if Alice draws her own name, there's just 2 different ways in which Bob, Charlie, and Dennis can avoid drawing their own names as well. Well, we picked out Alice to be special. Well, the same thing could be argued for Bob being the special one out, Charlie or Dennis. So we have to multiply this total number of ways in which there's one person out of the 4 drawing their own name by the number of people in the group, 4 times 2. So what happens if we have 2 self-draws in this group of 4 people? So say again, Alice is going to draw her own name. Then out of Bob, Charles, and Dennis, we need one other person drawing their own name. So in how many ways is that possible? Well, again, we did this before. This remaining group of 3, apart from Alice, if we want is one additional person drawing their own names, well, that's possible in 3 ways. Again, we have to multiply this again by 4 because we just took out Alice to be special, but it could also be Bob, Charlie, or Dennis to be the special one. But now we have to be careful a bit because we will be double counting. So if Alice is a special one and Bob is one of the 3 drawing their own names, we would get exactly the same outcome if we would have chosen Bob to be the special one, Alice being one of the 3. So we have to actually divide by 2. So multiply by half, and of course this gives us 6. And here, of course, we have 8 ways of having one person drawing their own name. So what happens with s equals 3? 3 people drawing their own names. Clearly, that's impossible with 4 people. But 4 people drawing their own name, well, that's exactly one possibility. So now we're left with s equals 0. So how do we find that? Well, we know that the total number of ways in which we can allocate these 4 names across the 4 different persons, that should be 4 times 3 times 2 times 1, or 4 factorial, which is actually 24. So we need the total here of number of ways to add up to 24. So if we look at this, we already have 15 accounted for, so the remaining 9 must be the remaining 9 possibilities in which we might have 0 self-draws among 4 people. So what about n equals 5 as a final example to look at? N equals 5. Again, we'll skip for a moment no self-draws as equals 0 among these 5 persons. So let's go at the number of ways in which out of a group of 5, just one of these persons is going to be the person drawing themselves, and the others will avoid, the other 4 will avoid drawing each other's their own names. So again, if Alice is a special one, Bob, Charlie, Dennis, and Eleanor will have to avoid drawing their own names. But we already know that out of this remaining group of 4, avoiding your own name is possible in 9 different ways. That's what we just computed. So we'll find a 9 over here. But this is taking Alice to be the special one who is the one who's drawing her own name. But that could be either Alice or one of the other four. So we have to multiply this again by 5. So this gives us 45 different possibilities for having one match here, one self-draw across this group of 5 people. For s equals 2, again, we can generalize in a similar way as before. So picking one of these people as a special one, Alice, then we're stuck with a remaining group of 4, out of which we want 1 to have a self-draw. So we computed that. One self-draw among 4 people that can occur in 8 different ways. We picked Alice to be the special one, but we could have picked anybody to be the special one. So we have to multiply this by 5, but again we have to avoid this double counting, so again we have to divide by 2. So that will give us 20 different ways of getting 2 self-draws. How about having 3 people drawing themselves? Well, that means taking Alice again to be the special one. 2 out of the remaining 4 should draw themselves. That's possible in 6 different ways. Again, you have to multiply this by 5, because Alice, instead of Alice being the special one, could have any of the other 4. But now we have a triple counting, right? So we have to divide this by 3. So that gives us remaining 10. Having exactly 4 self-draws obviously going to be impossible in a group of 5 people, and having 5 self-draws, that's just one possibility of having that. Again, we need to fill in the s equals 0, no self-draws row in this table, and we can do that by remarking that, well, in total there are 120 or 5 factorial ways in which you can allocate these 5 lots among the 5 different players. So this number of ways of drawing should add up to 120. So we already have 76. So 44 should be the number of available ways in which you can avoid having any of these 5 persons drawing their own names. So let's stop here at counting in groups. What we still need to do is fill in the probabilities. So if we know the number of ways, obviously we also know what the probabilities are. How do you do that? Well, by dividing this number of ways by the total number of different shuffles among this group. So in the first n equals 3 party, there's in total 6 different ways of allocating these lots among the 3 players, 2 of which, with probability 1/3, lead to no self-draws, 3 of which, probability 1/2, will have 1 person in the group of 3 drawing themselves. Probability 0 that exactly 2 people draw their own names and the third one doesn't, and there is probably 1/6 here of having all 3 people drawing their own name. With a group of size 4, we have 24 different options, so we have to divide the number of ways here by 24, 4 factorial, so we get 9/24 as the probability of having no self-draws, so that's actually equal to 3/8. We have 8/24 or 1/3 as the probability of having 1 self-draw, 6/24 or 1/4 of having 2, 0 of having 3, and 1/24 of having 4 self-draws. And finally, for the n equals 5 case, the total number of ways in which you can allocate the lots is 5 factorial or 120. 44 out of these lead to no self-draws, so the probability is 44 divided by 120, and that's equal to 11 divided by 30. Having 1 self-draw leads to 45 divided by 120, which is actually 3/8. For s equals 2, so 2 self-draws from these 5 people, 20 divided by 120, so that's 1/6. Probability 1/12 for 3, 0 over here, and 1 divided by 120 as the probability for all 5 drawing themselves. So these are the probabilities, and what we would like to do, of course, is go on and on until we reach higher levels of n. But we see this is a pretty laborious exercise. So what we need to do now is try to find out whether we can generalize this in a quicker way. So let's do that next. So let's have a look at this rule again that we use to compute the probabilities for having self-draws. So the rule that we used repeatedly is if we want to know the number of ways, let me denote that by a W for number of ways in which we can have S self-draws. So S might be one self-draw among a group of party goers which has size n. We argued or we used that we can write this as the number of ways in which S, we can have S minus 1 self-draws in a group which is one person smaller, so n minus 1. But then we have to multiply by n because the fixed person that we had left out, so the Alice person, could be any of these n persons. But we wanted to avoid overcounting, and to avoid overcounting means we have to divide this by S. So let's write this a little bit differently by multiplying both sides by S first of all. So if I multiply the left hand side, we see here S times the number of ways we can have S self-draws among a group of n, a party of n people, will equal n times the number of ways in which we have S minus 1 self-draws in a group of n minus 1 people. So it turns out to be convenient to actually rewrite this instead of in a number of ways in terms of the probabilities that we just introduced. And remember that probabilities were related to the number of ways in which some configuration can happen by basically multiplying by this n factorial. So the number of ways in which you can have S self-draws is n factorial times the probability of having S self-draws. So if we substitute that in this above equation over here, what we get is S times n factorial times the number of ways of having S self-draws in the group of n is n times, well then the corresponding thing, but now with a group of n minus 1 and S minus 1 self-draws, which would then be n minus 1 factorial times the probability associated to this group of n minus 1 individuals and having S minus 1 self-draws. Now why is this useful? Well, as you can see, we have on the right hand side here n times n minus 1 factorial, and if you think about this is actually exactly the same as n factorial. So 5 times 4 factorial, for instance, well that's exactly 5 factorial. So these two factorials basically on both sides are actually cancelling. So the rule turns out to be the general rule that we use all the time so far in constructing these ways or probabilities was S times the probability of having S self-draws in group n people equals the probability of having in a group of n minus people S minus 1 self-draws. So this is just a rephrasing of the abstract version, if you wish, of the rule that we use all the time in constructing these probabilities for all groups up to 5 people. But if you look at this in a general form, perhaps what might appear to you, at least what appears to me, and what makes my neurons fire, is well, this looks a lot. I recognize a pattern, and this pattern looks a lot like differentiation. So why do I see this as kind of a differentiation? Well, consider we have a function of some x. And this might be a polynomial function, so it might involve, say, a polynomial, a power of x to the power s, which might be multiplied by some coefficient as, and there might be some other terms in this polynomial. If I take the derivative of this function f, what do I get? Well, I get these other derivative of these other terms, but in particular over here I will get The S is going to come down. I'm going to multiply by S. The AS remains in place. And the power is coming down. That happens when you do, obviously, when you do differentiation. So if I compare these two structures, it seems to me that actually if you identify these coefficients, which are called here AS, with these probabilities, then this is exactly describes the rule that we found for these probabilities. So let me work this out first in concretely for the cases that we did. So what I want to do is I want to assign the probabilities that we just computed for these groups of 3 people, 4 people, and 5 people. I would like them to assign the role of coefficients in a polynomial. So let me do that for the group of 5 people, for instance. I want to construct a polynomial associated with a group of 5 people, a polynomial of some x, which is basically some auxiliary variable. So what were these probabilities? Well, the probability of having no self-draws, so s equals to 0 in the group of 5 people, that turned out to be 11/30, right? That's what we just found. So that will be the coefficient in front of the x to the power 0, or the constant if you wish. The probability of having one self-draw for in a group of 5 people, well, that turned out to be 3/8, that's what we saw. So that's I'm going to assign that the role of being the coefficient in terms of x to the power 1, or just x. The probability of having 2 self-draws in a group of 5 was 1/6. So I'm going to multiply that by x squared, so x to the power 2, 2 self-draws. And the probability of having 3 self-draws was 1/12. X to the power 3, number of self-draws. The probability of having 4 self-draws in a 5-person party was 0, so there's no x to the 4th here, but there is an x to the 5th, of course, which will be 1/120. The probability of having exactly 5 self-draws times x to the 5. So I'm associating this polynomial with the probabilities of the group of 5 people, and now my claim is, if I'm going to take the derivative here, I'm actually going to precisely use this rule. I'm going to implement this rule, and I hope to get actually at a similar polynomial, but now for 4 people. So let's see whether that works. So I take the x derivative here of that thing. So what do we get? Well, of course, the constant is going to vanish when I take the derivative with respect to x. So the first term here will be, well, the derivative of the 3/8 times x, and it's going to be 3/8. The second term will be twice the 1/6, which is 1/3 times x, so the power is going down from 2 to 1. Third term is going to be 1/4 times x squared. And then we'll finally have 5 divided by 120, that's again 1 divided by 24 times x to the 4. And indeed you can check by looking back at our previous computation. These are exactly the probabilities for having 0, 1, 2 or 4 self-draws in a group of 4. So indeed, by applying this derivative to this polynomial associated with the 5-person game and the 5-person party, we'll actually obtain the corresponding polynomial for a 4-person party. So obviously we can carry on. If I again take the derivative, I hope to get the 3-person probabilities. Let's check that. So the first term will obviously be 1/3. Then we'll have twice 1/4, which is 1/2 times x, plus 1/6. 4 divided by 24, 1/6 times x to the power 3. And indeed, these were the probabilities associated with having a group of 3 people having a party where with probability 1/3 nobody draws themselves, probability 1/2, so 3 out of 6 times one person is going to draw themselves, with probably 1/6, so there's one possible shuffle out of the 6 different ones. All 3, Alice, Bob and Charlie, are going to draw themselves. I can actually carry on and verify that this also makes sense for even smaller groups. So we can actually go down further from the 3-person party towards a 2-person party, and again taking the derivatives, we find, as perhaps anticipated by you, probability half of having no self-draws, when the other probability half having 2 self-draws. With 1 person, sad party, there's only the probability that you draw yourself, obviously, if Alice has her own party. And we might even go on to having a 0-person group, so no one having a party. Well, then with probability 1, no one is going to draw their own name from the hat. So we can even extend this down to 0. So if we look at these polynomials, we can observe 2 things. Well, one is that the sum of all these coefficients is for each particular group of n party goers is going to be 1, right? Because this is the sum of the probabilities of having some number of self-draws. We want these probabilities to add up to 1. So in terms of these polynomials, what this translates into is, for any n, if I substitute x equal to 1, basically all these powers of x are going to be set equal to 1, and I'm just adding up these probabilities, so that should be equal to 1, and that's indeed verified if you look at each of these polynomials. Second thing to observe is, what we're interested in is the probability of having no self-draws, which is essentially the constant term, the coefficient if you wish, multiplying the x to the power 0, the constants. That's the thing that we are after. That's the probability of having no self-draws, and we can find that by plugging in x equals 0. So if I plug in x equals 0, if I have the polynomial, I find what I was after, namely this probability of having no self-draws. So we're going to use this to actually do what we want to do. So note that here we are actually going from large groups to small groups. So again, we started at a big group of 5 people, we took derivatives, we figured out, oh, well, then these must be the probabilities associated with the groups of smaller size. What we like to do is go up, go in the other direction. We want to increase the number of players. Well, we could do this, of course, by reversing the process of taking derivatives. So formally, that's finding the primitive. So let's have a look. So if we start with the lowest group, n equals 0, no people, the polynomial here is just 1. Can I find a function which, if I take the derivatives, gives me 1? Well, of course, yes, we can, and x indeed satisfies the job. Also, if we plug in x equals 1, indeed, this nicely satisfies the condition that when evaluated at 1, this function evaluates to 1 itself. Going up once again, if I want to find a function which, if I take the derivatives, yields x, what I would obviously find would be a half x squared. So a half x squared, if I take the derivative, we find x. But this itself does not satisfy the condition that if I plug in x equals 1, it adds up to 1. But I fortunately have a little bit of freedom of adding a constant, and the constant that I need to add indeed is a half. So I could go back here, sort of keep on sort of finding functions which, upon differentiation, yield me the next polynomial. So here a half would integrate to a half x squared. So we need to use the function 1/6 x cubed. But again, we want these coefficients to add up to 1. Or in other words, if I plug in x equals 1, I want the function to evaluate to 1, and that determines the size of this constant. And I could go on and on. I could even go beyond the polynomial of this group of 5, but you see this is actually still pretty laborious and not that quite different from what we are doing before. It's just a different way of writing this down, but each time I will still have to find this constant coefficient by making sure that everything adds up to 1. So the question is, can we speed this up a bit and actually generalize in such a way that we don't have to, in order to find the coefficients for a group of 1,000 people, we don't have to do this same procedure 1,000 times explicitly. Unfortunately, we can. So the trick that we're going to use to actually speed this process up is by recognizing that any function of x, you can also, a polynomial in terms of x, you can equally well describe as a polynomial in terms of powers of x minus 1, and vice versa, since if you have a particular power of x minus 1, say x minus 1 squared, for instance, we can of course always rewrite this by expanding into, in this case, x squared minus 2x plus 1. So if you have a polynomial with powers of x minus 1, we can rewrite this in terms of a polynomial with just the powers of x, and vice versa. If we have a polynomial in terms of powers written in terms of powers of x, we can rewrite this in terms of powers of x minus 1. So why is this useful? Well, let's try this and we'll see what happens. So let's start again at f0, which was equal to 1. And let's again do the inverse of the differentiation. So if you wish, finding the primitive of 1, but now instead of using x, I'm going to write things in terms of powers of x minus 1. So what function actually will provide 1? What function of x minus 1 will provide 1 if I take a differentiation? Well, obviously that's the function x minus 1. If I take the derivative of x minus 1, I will get my 1. Does it work? Well, almost, except that in this case, if I plug in x equals 1, it doesn't evaluate to 1 as we wanted it to, but to 0. So we have to add a constant to this. And we can always add a constant if when finding a primitive function. And the constant that we need to add, obviously, is 1. And indeed, if you work this out, this is again this function x, which we had before. So we get exactly the same answer, but now through this root of x minus 1 instead of x. What happens if I go to the next level, a group of 2 people? Again, I have to find a function in terms of powers of x minus 1, which upon differentiation will yield me this particular the one-person group polynomial. But to get the 1, I need the x minus 1, of course. To get x minus 1 itself, I need a half times x minus 1 squared. Do I need a constant? Well, I again want to make sure that if I plug in x equals 1, this function evaluates to 1, adding up all the probabilities. But again, these two terms here add up to 0, because x minus 1 equals 0 when x equals 1. So again, you have to add 1. And now you see the pattern emerging. All these powers will automatically evaluate to 0 when I plug in x equals 1. So I will always have to add a constant equal to 1. So that makes life a lot easier. So let's do it for the 3-person group. I will get, to get 1, x minus 1. To get the x minus 1, I'll need a half times x minus 1 squared. To get a half x minus 1 squared, I'll need a 6, or 1 divided by 3 factorial, x minus 1 to the power 3. And again, to make sure that if you plug in x equals to 1, the function evaluates to 1, we need to add 1. Now we see that the pattern is clear. Actually, we can actually generalize this all the way for general n. For general n, we'll find an n-person group the corresponding polynomial will turn out to be 1 plus x minus 1 plus 1 divided by 2, or 1 divided by 2 factorial if you wish, x minus squared, plus all these other terms until we arrive at 1 divided by n factorial times x minus 1 to the power n. So this is the polynomial expression that will lead to the probabilities for the n person party. But in order to find these probabilities, we need to figure out, well, what are the corresponding probabilities if I expand all these powers. Well, in particular, since we are particularly interested in the 0th order, or the constant term, we need to evaluate this thing at x equals 0. So the probability of s equals 0, so having no self-draws, which was the thing that we were after, that would be equal to fn with 0 plugged in for the x. So what do we get? If I plug in x equals 0, 1 minus 1 plus 1 divided by 2 factorial minus 1 squared plus all these other terms plus 1 divided by n factorial minus 1 to the n. Or in other words, 1 minus 1 plus a half minus a sixth plus 1/24 all the way up to plus 1 over n factorial times minus 1 to the n. So this is indeed the sought after probability of having no self-draws in a group of n people. So do we recognize this thing? In particular, when n goes to infinity, well, some people might recognize this as the expansion, this thing as the expansion for e to the power minus 1. So the constant, the 1 divided by e, that we found experimentally in the computer experiment at the beginning. Some might also actually recognize the expression over here. So if we take the limit of n going to infinity, we call this f infinity of x. This is going to be the limit of the expression that we have over here, the sum of n equal 0 to infinity of x minus 1 to the n divided by n factorial, the sum of all these terms. And this exactly is the expansion, or the definition, if you wish, of e to the power x minus 1. So if we want to know again what the probability is of having 0 self-draws, so everybody draws somebody else, we have to plug in x equals 0, and again we regain this e to the power minus 1.